Okay, very good. Um, Today is 12 degrees warmer than a week ago. So I think it's been the coldest day of the winter so far. And so we are now coming to many lecturers take the liberty at the end of the course to talk a little bit about what they find most interesting. This is what I'm going to do today. I've been thinking about where, so the machine learning is going to really change most subfields of science, I think, that's for sure. It's going to change the world outside the sciences. I've been thinking, where do I expect or where am I going to look closest at what it is going to do? I think one is artificial general intelligence for sure, because progress there sort of implies progress in any of the other fields. And there is, okay, and there's of course the big question, will it reach human level, and if so, how soon? And the expectations of can it do that at all and on what time scale can it do it, they differ very widely between experts in the domain. So that's quite interesting. The second field where I think we will see major changes in the real world is a closer integration of AI and robotics. So right now we have pretty good robotics. We start to have good AI, but the two have not really come together yet. And when they will, I think this will really change the way, well, it will for sure change, well, I think that has the potential to change society quite a bit also in many ways. And the third sounds maybe less dramatic, but it's the one that I find most interesting, namely what machine learning can do in the molecular world. Molecules are amazing machines. And well, before Christmas, we were discussing a little bit, what does a single cell do? And we have not even understood a single cell. And a single cell is a collection of formidable molecular machinery, which we don't understand very well yet. So they're very small and they're very versatile. Yeah? So we can have molecules that extract rare earths from trash and whatnot, or let's say small organisms. All of this is not understood yet, which is the scientific side. All of this can potentially be engineered to make it work better for our purposes. So understanding or being able to make predictions about larger molecular systems than we can today, that seems to have big potential to me. And it raises interesting scientific questions also. And when we want to predict properties of molecules, there is a range of possible descriptions that we can, or representations that we can use. We can, on the course level, just describe molecules by strings. And that, so for example, something called SMILES strings, and that gives access to large language models and the like. Or we can represent especially small molecules or simple materials by fingerprints and then use those in old school machine learning. Or we can really characterize by molecules by the positions of atoms in space. And that's the representation I want to talk about today. And using this kind of representation, so I'm going to call it atomistic machine learning here. We have a whole range of methods that we can use. And I'm writing on these axes the logarithm of the cost. And when I write cost here, this is vague. It's a mixture of what's the computational complexity of a method and what is its prefactor. And up here, I write the accuracy. And well, as you would expect, more accurate methods are more expensive. And so broadly, we have, you can expect this kind of band here. Unfortunately, the cost is given on the logarithmic scale and the accuracy is given on the linear scale. So yeah, if you want to be extremely accurate, it's going to become extremely expensive. And if I did annotate this with computational complexity, then we would have, I'm giving here the formal complexity n to the 3, n to the 4, somewhere we have n to the 6, n here being the number of atoms or number of electrons in the system. And we have methods like Hartree-Fock. We can have a perturbation theory. We can have coupled cluster methods. We can have further out something called configuration interaction. These all invoke the laws of quantum mechanics. Here sits an interesting one, density functional theory, which we'll talk about more today. And then somewhere here, effectively, okay. So here it's all more or less linear, but still there are different levels of approximation. So we might have semi-empirical methods here. I'm abbreviating semi-empirical, that's still quantum mechanical methods. And then we have classical force fields. So here bonds are represented by harmonic springs, and angles have very simple potentials and so on. And even simpler than that, we can start coarse graining. So we can say we don't represent, for example, each atom in an amino acid, but the whole amino acid becomes one unit. And then beyond that, we have continuum models. And I want to, okay, and here I don't have enough space to write, but what I want to write here is interatomic potentials, or I'm writing machine learned force fields. So there are two outliers in this band. And I think the one outlier is DFT, because DFT is not where it should be, but it has accuracy more or less comparable to that of MP2, if you're lucky, better. So this is where DFT sits, density functional theory. And those force fields, they really use the, chemists draw molecules and they have forces acting only wherever a chemist drew a bond. These machine learned force fields, they use a richer neighborhood. So the machine learned force fields, each atom sees everyone in the local neighborhood. So they are more expensive, and also because they use this machinery that we discussed last time, equivariant neural networks and such. So they're more expensive than force fields, but they're surprisingly good. So I would put there, so let's say in narrow regimes, yeah, if you train them, if you use them on exactly the data that you've trained them on, you can make them as good as DFT or maybe better. If you use a single force field that has been trained on a much, much bigger data set, not just your systems of interest, it might be here. And well, if you go out of distribution, you might be here. Yeah, but so if you train those on your system of interest, and if you use them on your system of interest, these can be extremely good. So the two outliers here are as marked, and this one here uses these equivariant neural networks, rotation equivariant neural networks that we have been discussing last time. And this so far has been a pure quantum mechanical method, no machine learning involved. But, and now this is coming to the work in my lab, we are seeking to infuse this with machine learning, and we hope we can keep this accuracy, but make it cheaper. Yeah, so we hope to end up somewhere here. Yeah, and this is and how we are trying to do this is the topic of today. So I want to introduce you to density functional theory. Or DFT for short. And it has two notable theorems. Those are due to Hohenberg and Kohn. And Kohn, by the way, okay, I'm coming back to a picture that I drew at the beginning of the course. Okay. Kohn, so you know, what are we doing here? We're using, on the one hand, the notions of density functional theory, and this is what Kohn got his 1998 Nobel Prize in chemistry for. And on the other hand, we have now our 2024 Nobel Prize in physics. And basically, we are combining ideas from these fields to try and go from here to here. So Kohn got the 1998 Nobel Prize for two contributions. On the one hand, these celebrated theorems, and on the other hand, then a practical method that made these theorems work. Just curious, who has heard about Hohenberg-Kohn theorems? All right. In a solid state lecture, or where was that? Yeah? Good. All right. So what it states in words is that if we have electrons interacting in some external potential, then that potential is uniquely determined by the ground state density. And I'm not going to write it in words. I'm just going to put a picture here. So what we have had traditionally is that if we have an external potential, then we can construct our molecular Hamiltonian from it. So the molecular Hamiltonian, it has a known operator for the kinetic energy. It has a known operator for the electron-electron interaction, and it has an operator representing interaction of the electrons with this external potential. And from this Hamiltonian, by solving Schrödinger equation, we can get the many particle wave function. I'm only writing R because I'm omitting spin today. And from this wave function, we can get the density. So we can get the ground state wave function, and we can get the ground state density. The ground state density is just n times the one. So it's here the one particle electron density. So if I have R, R2, and so on up to Rn. And then I'm sorry, I started too far on the left. And then I integrate over all variables from R2 up to Rn. I'm left with something that depends on the single variable R. Okay, this is my one electron density here. So this has always been known. This is just standard quantum mechanics. And what's new now is that this Hohenberg-Kohn theorem establishes that the density uniquely determines the potential. And the proof is actually surprisingly simple. And I'm not giving it today because it would take too much time away from the machine learning that I want to talk about. But I can make a qualitative argument for you. So this is an observation by the scientist Wilson. So when the Hohenberg-Kohn, when they first presented their theorem, this was in some meeting, he stood up and said, yeah, okay, of course, we've been knowing this all along. And he was arguing as follows. If you give me some electron density, so I'm here plotting a one-dimensional electron density. So this is R, and this here is N of R. Then, well, the integral of this density gives me the number of electrons. I can just integrate it over space, and I see how many electrons there are. And the cusps in this density, in a ground state density of molecular systems, we have these sharp cusps. The cusps tell me where the nuclei are. And the height of those cusps, or I can also look at the derivative of the density around those cusps. The height of the cusps is going to tell me what is the charge at that nucleus. And if I know the charge of the nucleus, I know what element this was. So, for example, I could infer that this must have been a fluorine and this must have been a hydrogen. And this is the molecule HF in this case. Okay, so that's the qualitative argument. And then Hohenberg and Kohn made a more theoretical argument. That's the Hohenberg-Kohn theorem number 1. And the Hohenberg-Kohn theorem number 2 is a variational principle. Namely, that we have a functional of the density, and I am writing external potential here, but I could also omit it by virtue of Hohenberg-Kohn theorem 1, yeah? Because the density does imply the potential. So I'm just writing E of n here. And this variational principle says that if we minimize this over n, we are getting out the ground state energy associated with that external potential. And secondly, the ground state density is going to be the minimizer. Okay, and I'm writing these square brackets here because the electron density is a function of space. Yeah, so I could always write n of r, and the energy is just a scalar. But here we have a scalar which depends not at the density at a single point, but at the entire density across all of space. Yeah, so the square brackets here say we're talking about a functional, and of course this is much harder to learn than a function that depends on its input at just a certain point in space. Oh, all right, and this proof of the second theorem is also relatively simple, but I'm also not showing it today. Instead, I will give you the constrained search formulation, which came a little bit later in time, but is a bit more explicit than these proofs. So the constraint search formulation of DFT is due to Levy and Lieb. This was independent work. Lieb was a little bit later and fleshed it out in more mathematical detail. Yeah? So this was year 1979, 1983. Whereas the original Hohenberg-Kohn theorem, this was, I believe, 1967, 68. All right. And so why is this of interest at all? It is of interest because normally in quantum mechanics, or when we predict molecular properties, we take this, and then from this ground state wave function, we compute all the observables of interest. The most important one being energy, because the energy, for example, how the energy changes as I move around atoms in space. This tells me about vibrational modes, or about the I can then run molecular dynamics. Or if I look at how the energy changes as I switch on an external field, an electric field or a magnetic field, I can infer all kinds of properties from the wave function. But here, in generality, it is a joint function of all electrons, except if we start factorizing. Yeah? So in methods like Hartree-Fock, we make simplifying mean field approximations, but really it's a function of n electrons. Well, and in a protein we have a whole lot of electrons, so that's a beast of a high-dimensional function to try and calculate. And this is why up here so for DFT and more expensive, we can really look at small molecules. So DFT can, let's say, routinely do 100 atoms, or 100 heavy atoms, let's say. But the further you go to the right, so here we're often talking about, about 3, 4, 5 atoms. And here, going to the left, we're really talking about proteins in boxes of water. Yeah? And we would like to look at proteins in boxes of water, but at much higher accuracy than is possible today. And the great fascination here is that we now have something that depends on a single variable. This is just a function in space. And this is at the heart of this original formulation of density functional theory. And this is this formulation of density functional theory, where we just have the density as a function of space. This is today, to differentiate it from a different formulation, is also called the orbital-free density functional theory. Okay, so small excursion here. When I write here DFT, and when everybody says DFT, what we really mean is Kohn-Sham DFT. Okay, sorry. Should have said this maybe a bit earlier. Yeah. So in DFT, we have these two formulations. There is the original one, which centers just on the density. And this today is called the orbital-free formulation. Or you can also call this pure DFT. And this is sometimes abbreviated as OFDFT. And then on the other hand, we have this Kohn-Sham DFT, or KS DFT. And this one here reintroduces orbitals. So we have here and you notice here that we have orbitals that describe what's happening to single electrons, and then we combine them to a multi-particle wave function by means of a Slater determinant that does the anti-symmetrization for us. And right now, so this Kohn-Sham DFT, it reintroduces orbitals for a reason that I will explain later. And well, this method has a nominal complexity if we use density fitting of n to the 3. The complexity here is unknown. And this is what most people use today. Yeah? So if we look at how many people do the one versus the other, then 99.999% of all computations use this Kohn-Sham DFT, and 0.001% use that formulation. Why? Because there has been a missing ingredient so far, yeah? And we are setting out to learn this missing ingredient. And so from around 3 years ago, the estimate was that this Kohn-Sham DFT, so it's difficult to come by hard numbers, but one serious estimate that I've read is that 30% of the worldwide supercompute went into this. Yeah, and I'm quoting here. That's a number from 2021. I think this is dropping now because large language models are eating up so much more supercompute. So this prediction of molecular properties by means of Kohn-Sham DFT, this is a big business. Yeah. All right. So this is why we want to look at this orbital-free version, because we hope to get lower computational complexity out. All right. And now to understand what this orbital-free DFT is, I will want to look at the Lévy-Lieb formulation with you.